So recall back in chapter 4, we asked you to do problems like this, right? Where we asked you to find the exact value of sine inverse 1/2 without using your calculator. So whenever you see exact value, you should be thinking unit circle in this kind of a class. So we remember that the range for sine inverse was negative pi over 2 to positive pi over 2, which basically means we're looking in quadrants 1 and 4. So if I go to my unit circle and I look in quadrants 1 and 4, the only place where the y-coordinate is 1/2 is there at pi over 6. So that should be my answer, right? Is everybody okay with that process? You remember doing that? So looking at the unit circle, we get pi over 6. Now, the next type of problem that we looked at in chapter 4 was a problem like this, but then we tacked on the extra, like, you know, from like pi over 2 to 3 pi over 2 or something, right? So it's the same idea. We use this to look at what quadrants we'd be covering. So that would be quadrants 2 and 3. So we look on the unit circle in quadrants 2 and 3 for the place where the y-coordinate is 1/2. We get that 5 pi over 6 should be our answer. Okay, so that's kind of what we did in chapter 4. What we're going to do here in chapter 5 is take this same kind of question, but what if we don't give an interval? What if we don't give an interval? How many answers is this going to have? We know it has at least 2, right? We know it's at least pi over 6 and 5 pi over 6, right? Because both of those, if I do sine of them, give me 1/2. Are there more than just those 2? What do you guys think? Yes. There are lots more. How many more? Lots and lots and lots more. Infinitely many more. Why? Because any angle coterminal to pi over 6 will also give me sine inverse of 1/2, or will give me sine of that angle equal to 1/2. And any angle coterminal to 5 pi over 6 will also satisfy the equation sine theta equals 1/2. And how many angles do we have coterminal to pi over 6? Infinitely many. How many angles are coterminal to 5 pi over 6? infinitely many. So how many answers is this equation going to have? Infinitely many. Can I write them all down? No. So we need to create a notation to kind of describe these infinitely many solutions. Keep in mind that this is not the same thing as like all real numbers being a solution, right? Any angle will not satisfy sine theta equals 1/2. Only specific angles will. Now there's infinitely many of those. So the way we're going to describe them is just kind of like we said aloud. We're going to say, okay, well, x could equal pi over 6, and then anything coterminal to it. So how do I write anything coterminal to it in symbols? We say plus 2 pi k, where k is an integer. So that's just the notation of saying pi over 6 and anything coterminal to it. And then we can say the same thing about 5 pi over 6. Is everybody okay there? So again, that notation at the end just means and anything coterminal to it. So anytime you answer one of these trigonometric solving questions and the interval is not specified, you're to assume the interval is all real numbers, and you're going to list, the answers on the unit circle and then anything coterminal to them. Everybody so far so good? So the other thing, in addition to giving you problems that we don't specify an interval on, we'll be giving you intervals where maybe you can get more than one answer coming out. So let's look at this example. So here it's the same question, sine x equals 1/2. But here we're told we're looking for our solutions from 0 to 2 pi. Notice that's like the entire unit circle. So all I'm going to do is look on the entire unit circle for where the y coordinate is 1/2. Well, what are those two values? Pi over 6 and 5 pi over 6, right? Or alternatively, if I took my answer from up here, and said just let k equal 0, I would just get pi over 6, right? Or if I took the other answer, 5 pi over 6, and again let k equal 0, I'd get just 5 pi over 6. Again, those are the two answers that I'm looking for. The takeaway here is that this general solution I can use to generate all solutions to any equation regardless of the interval that they're asking me to solve for. If instead it asked for like 0 to 6 pi, well, k equals 0 gives me a solution. Then I'll try k equals 1 and see if that falls in the interval. Then I'll try k equals 2 and see if that falls in the interval. Then I'll try k equals 3. And I'll just keep going until I get start getting answers that are too big. Or I could go the other way and keep going until I get answers that are too small. Is everybody okay with that idea? So this general solution here is going to be kind of our skeleton key to unlocking any solutions over any interval that we so desire. So the other thing we'll see are in the homeworks and whatnot are intervals that contain more than one solution. Could be multiples, like this one had 2 solutions. They could be 3, 4, 5, 6, 7, depends on the size of the interval you're solving over. Is everybody okay with that? The other new thing that'll happen is that maybe your problem won't be ready-made to go to the unit circle. Like maybe you might have to do some algebra to it before we can go to the unit circle. So let's take a look at this one. Here we have cosine squared x equals 1/2. Now, before I can go to the unit circle, I have to have just sine or cosine or tangent or cosecant or secant or cotangent. Just those things. No coefficients, no exponents, nothing added or subtracted to it. It has to be all by itself on the left side of the equation. So what do I need to get rid of on this left side before I can go to the unit circle? The exponent. Good. How do I get rid of a squared? We square root both sides, right? Now remember, when we square root both sides of an equation, what do we need to do? What happens when we square root both sides of an equation? Yes, we get a plus or minus. So we'd have cosine x equals plus or minus 1. So before we'll go to the unit circle, we'll rewrite that as 2 separate equations, cosine x equals 1, and then cosine x equals -1. And then we're going to go to the unit circle and look for where the x-coordinate is 1. And go to the unit circle and where the x-coordinate equals -1. And because the interval we're solving for is from 0 to 2 pi, I'm just looking at the unit circle, right? Now, notice here that the 2 pi has a parenthesis on it, so 2 pi is not a viable answer to us, but 0 is, because 0 is the bracket, right? So let's go to our unit circle. So I'm looking at places where the x-coordinate is either 1, so I see that here at 0, and I go around, I see it's -1 here at pi, I go around, and I'm back at 2 pi now, but I don't need to include that because 2 pi is not in my solution space, right? The interval was from 0 to 2 pi, not including 2 pi. Josh? Yep. So I'm just looking at the unit circle where the x-coordinate is 0, or x-coordinate is 1. So I see it here. So that solution is going to be 0. So I keep on going, looking for either x-coordinate 1 or -1. Oh, I see another one here. It's -1, so the other solution is pi. And then I'll keep going, looking at my x-coordinates. And I'm back here. This would be 2 pi now. But the problem is only asking me to go from 0 to 2 pi with not including the 2 pi, so I know I'm done. Okay? So here we got x equals 0, and here we got x equals pi. Is everybody okay with how I pulled those from the unit circle? Okay. Let's do another. All right. What if we have this time 3 tan squared x equals -1, or I'm sorry, equals 1? What's wrong with the left-hand side here? We have a coefficient of 3 and an exponent squared, right? Which one do we need to undo first? The exponent or the coefficient? Nope. Yeah, we got to get rid of the coefficient first. Remember, when we're solving, we're following the reverse order of operation. So we want to undo it, adding and subtracting, and then multiplication, division, and last exponents, right? It's the reverse of order of operations. So we'll divide by 3 to both sides. And then we'll square root both sides. And remember, what does a square root do for us? Makes a plus or minus. Now remember, tangents are going to be the ones that are kind of tricky to find on the unit circle, right? So I'm going to do a little bit of simplifying here. So the square root of a fraction is the same as the square root of the numerator over the square root of the denominator. I know the square root of 1, well, that's just 1. And I know tangent is y over x, right? So if I go and I look at my unit circle, there's no place on the unit circle where the y-coordinate is 1 and the x-coordinate is square root of 3. But I do see a place on the unit circle where the y-coordinate is 1/2, 1 over 2, and the the y-coordinate is 1/2, and the x-coordinate is square root of 3 over 2. So I can make that work with what I got. If I just multiply the top and bottom of this by 1/2. Okay, there. All right. So we have this then, right? So I'm looking for the places where the y is positive or negative 1/2, and the places where x is positive or negative square root of 3 over 2. Everybody's okay with that? So let's go to our unit circle and start hunting. So we have here at pi over 6 should work. And then here at 5 pi over 6. And then here at 7 pi over 6. And then here at 5 pi over 3. Oh my goodness, no, not there. At 11 pi over 6. Good, great gobs of goo. Gonna go for guts. The y was the one, plus or minus 1/2. Oops, a daisy. And then we've gone around one full time, so we've caught them all between 0 and 2 pi. We're all set. So I should have 4 answers 5 pi over 6, or I'm sorry, pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. And this is like kind of just bad notation and silly, like shouldn't have x in two different places. Maybe we should just call that theta from the jump. It's probably confusing to go back and look. One x is the variable that's an angle, another x is a coordinate. We have two x's that mean two different things. That's some bad notation there, Mr. Kulik. I concede, yes. Not great. So far, so good? Not much different than what we did in chapter 4, right? It's like the next logical step forward. What if I have something like this? So 2 cosine squared plus cosine x plus 1, equals 1. Oh dear boy. What does this thing kind of remind you of? When you look at this equation, what does it kind of remind you of? Yeah. Maybe, but not for here. So when I look at this, the thing that I see is I see something squared, something to the first, and then a constant. It's almost like if I say y is cosine x, this would be like 2y squared plus y equals 1. What type of an equation is that? You would have studied it a whole heap of time last year in Algebra 2. It has a name. Starts with a Q. Quadratic, right? What are the different ways you have to solve a quadratic equation? Give me one way we can solve a quadratic equation. No, that's a system. You could use the quadratic equation or the quadratic formula. Yes, that's one. What else? Oh, guys, come on. How about factoring? What else? Okay, sure, you could do graphing. Don't love it, but sure. That's valid, always valid for any equation, not just quadratics. How about completing the square? That's a technique you could use. And then, depending, you might be able to use a radical, right? If it's just like, the previous one, where technically that's quadratic, because there's only a squared term, you can just use a radical on it. Here we have a squared term and a linear term, so the radical's out, right? Which one of these is the most tedious to do? Okay. Tied for that, though, would be, you guys remember doing completing the square? That was a hassle, right? Like, I don't want to do that. So we're really between factoring and the quadratic formula. You guys agree? Which one did you prefer? Okay, so let's say we do this with the quadratic formula. In order to use the quadratic formula, what's my starting condition? If ax squared plus bx plus c equals 0, then x equals negative b plus or minus square root b squared minus 4ac all over 2a. Right? That's your statement for the quadratic formula. If we go look at our equation, do we meet the initial conditions? No, why not?
The 1's on the other side.
Yeah, it's equal to 1 and not equal to 0. How do I fix that? You just got to subtract 1 from both sides. Why does that matter, Mr. Kulik? Well, it matters a lot. Is it's going to change our value for C, right? All right, what's our value for A? Two. What's our value for B? Okay. And what's our value for C? Negative 1. So we can say then y equals negative 1 plus or minus square root 1 squared minus 4 times 2 times negative 1 all over 2 times 2. What's 1 squared? 1. What's 4 times 2 times negative 1? Negative 8. What's 2 times 2? Okay. What is 1 minus negative 8? What's the square root of 9? How do I do negative 1 plus or minus 3? Is that just plus or minus 2? No! You have to split it, right? So you do negative 1 plus 3 and do negative 1 minus 3. So my two solutions would be 1/2 and negative 1, correct? So far, so good? Okay, so we have y equals 1/2 and then y equals negative 1. But go back to the original problem. What were we trying to solve? Was our original equation 2y squared plus y equals 1? No, what was the original? It was 2 cosine squared x plus cosine x equals 1. And what did we do? We just let y equal cosine x. So guess what we have to do now? Plug the cosine x back in. And now I'm ready to go to my unit circle. So in the first equation, I'm just looking for where x is 1/2. And in the second equation, I'm looking for where x is negative 1. Everybody, so far so good there? All right, I'm going up to the unit circle. Here I go. Actually, let me just bring it down. Oops, that's more than I wanted to take with me. All right, so we're looking for where x is 1/2. So if I look, pi over 3, and 5 pi over 3. Everybody feel good there? Again, the interval we're solving for said 0 to 2 pi, so I'm only looking on that once around the unit circle. And then the other place we're looking for now is where x is -1. So aha, pi, oh, that's the only one. So that had 3 solutions. That feel okay there? So far, so good? Okay. So notice this equation. Notice 2 things different about this. One, there's no interval given to me, right? What does that mean we're solving for? We're going to have infinitely many solutions, right? So we're going to have to do that plus 2 pi k thing to the end. No big deal, but want to recognize that from the start. The second, if I look at my equation, it's the first time I've seen 2 different trig functions going on in the same equation, right? So when I see that, I'm going to need to do one of 2 things. One is I could look for an identity so I can change them all to be the same trig function. Now, can I rewrite tangent so it's just sines? Do I have an identity that does that? I do not, right? Tangent is sine over cosine or secant over cosecant, but I don't have anything that's going to turn it into a sine. How about the other way around? Do I have anything that's going to turn sine into just a tangent? No way, Jose. So an identity's out. The other option then is that maybe I can do some factoring where I can separate out my trig functions into their own separate factors. That's going to be the route that we're going to have to go with. So the first thing I want to do if I have to go this factoring route is get everything on one side of my equation. So I need my equation to equal 0 because to solve a factoring problem, I have to employ the 0 product property. So my equation has to equal 0 if my plan is going to be to solve by factoring. It's a necessary first step. So far, so good. So if I look at that left-hand side, I have 2 tan x sine x minus tan x equals 0. How can I factor that? Do I see any squareds? So it's not going to be like a quadratic factoring. right? What's the other type of factoring we can do? Least common multiple is the other type of factoring. So if I look at this term and I look at this term, is there anything in common between them? What is in common? Tan x. So I'll factor a tan x out. What does that first term become when I factor the tan x out of it? So what does this become? Two sine x. Very good. Remember that when we're factoring these out, it's like we're dividing. Jackson, go ahead. Okay. What does this become? 1. Is everybody okay? So now, if I look at my factors, one factor is tan x, and the other is 2 sine x minus 1. Have I separated the trig functions into separate factors? I have, right? So now when I apply the zero product property, this becomes the two separate equations, tan x equals 0, and then 2 sine x minus 1 equals 0. Is everybody okay with what I've done so far? Does this look like the factoring that you would have done in solving by factoring like in Algebra 2? Except we have trigs mixed on top of it. Okay. So this guy, the tan x equals 0, the trig function's already isolated by itself, right? So we're ready to go to unit circle. We're looking for where y over x is equal to 0. Well, what does that, if y over x equals 0, what does that mean? It means y equals 0, and x can be anything other than 0, right? So I'll go to my unit circle and look for the places where y is 0, and hope that x isn't also 0 there, right? So let's see. I have a y equals 0 here. X is 1, so that's okay. So I have my solution 0. Looking at my y's, there's the next place where y equals 0. X is not 0 there either, so my solution should be 0 and pi if I keep going. There's no other place where the y coordinate is 0, so I'm done with that one. So I'm going to have 0 plus 2 pi k, where k is an integer, and then 0 equal, or and then x equals pi plus 2 pi k, where k is an integer. So that's one set of my infinitely many solutions. Now I have to solve the other equation. 2 sine x minus 1 equals 0. That one, the trig function is not by itself yet, so I have to do some algebra to it. What should I do first? Add 1 to both sides. And then divide by 2. Does it have to be in that order? Yeah, it probably needs to be in that order. I mean, unless you're being super duper careful, and I don't trust any of us that we'd be so careful to do it in a weird order and get the right answer to come out. So I'm going to go to my unit circle and look where y equals 1/2. So I'll go back to my unit circle. I'm looking for where y is 1/2. I see it here at pi over 6. Here again at 5 pi over 6. And those are the only times on the unit circle I see it. So those are the two that I need. But again, we're looking for infinitely many solutions here, so we have to slap that 2 pi k on at the end. So that's what my solution set here would look like. Now, just as a caution, this answer is completely correct, but there's a simpler way to write this. So look at these answers. That first solution would be 0, 2 pi, 4 pi, 6 pi, 8 pi, right? The second set of answers would be pi, 3 pi, 5 pi, 7 pi. What do you notice there? If I put them together, I'd have 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, etc. So a simpler way to write this would be that x is equal to pi plus, or I just write it as x equals pi k, where k is an integer. Now, do you need to do that? No. But if you're looking at the solutions, I probably wrote it in the simplest way possible, so it took up the least amount of space when I wrote the solutions, the solution sets. So don't be confused about that. Just double check to make sure that the things generated by your solution and the things generated by the textbook solution match. As long as they match, you're fine. You don't have to write it the same way the textbook does. Okay? Does everybody feel okay there? Just want to point that out. Let's do another kind of like this one, eh? What do you say? All right. So it wants all the values of x on the interval from negative 4 pi to 2 pi that satisfy the equation sine squared x equals sine x. First thing I'm going to notice, it's a pretty big interval, right? That's 6 pi long. I'm expecting a bunch of solutions here. So I'm definitely going to find the general solution, then plug in values for k. Everybody's all right with that idea? So just pointing things out that I'm seeing. The second thing that I see is that I have a quadratic here, all in terms of signs, right? So to solve that equation, this is a quadratic that doesn't have a constant term to it. By far, the easiest method for this is going to be factoring. Don't use a quadratic formula on something that is this simple. So we'll just subtract the sine x over. Because as long as it's a quadratic with no constant term, the factoring is just going to be a least common multiple factor, right? What is in common between sine squared and sine x? Sine x. So that's what I'll factor out front. What does sine squared become when I factor sine x off? Sine x. And what does sine x become? Everybody happy? So now that we factored, we apply the zero product property. So far, so good. The one on the left, sine x is isolated by itself, so I just need to go to my unit circle and look for where y equals 0. So if I do that, I have here at 0, and then here again at pi. So that's, if I translate those to my infinite solution version, I'm just going to slap that 2 pi k on them. And then I need to remember that this problem was going from, negative 4 pi to 2 pi. So I need to now use these guys to find the rest of my solutions, right? So if I say let k equal 0, I get x equals 0 plus 2 pi times 0, so just 0. And I get x equals pi plus 2 pi times 0, so pi. Is 0 and pi in between negative 4 pi and positive 2 pi? Yes, right? Each of those is on that interval. So those are going to be answers. Now, those answers are both smaller than 2 pi and bigger than negative 4 pi. So let's try it again. Maybe this time we'll say, okay, well, let's see if k equals 1. So 0 plus 2 pi times 1, that's 2 pi. And then I have pi plus 2 pi times 1, that's 3 pi. Is 2 pi in between negative 4 pi and 2 pi? It is. Notice that that 2 pi has the bracket, so it counts. But 3 pi is too big, right? Everybody so far so good? So I've either reached the very biggest that I can possibly have or gone over. So I know that any bigger k's are just going to give me stuff that's too big, right? Everybody can see that? So what I have to do now is start checking some negative k's. Because I can go all the way down to negative 4k. So if I say, okay, k is negative 1. That gives me negative 2 pi for the first one. Oops. And then negative pi for the second. Both of those are inside our interval from negative 4 pi to 2 pi, so those are good. Okay, so keep going. So that's going to give me negative 4 pi. And then negative 3 pi. Those are both good. Remember, negative 4 pi has the bracket on it, so that negative 4 pi still counts, right? And if I go smaller again, guess what's going to happen? They're both going to be too small, right? So I've exhausted all the solutions on this side. So I have negative 4 pi, negative 3 pi, negative 2 pi, negative pi, 0 pi, and 2 pi. I just wrote them in numeric order. It's out of order from the list, but I'm just anal retentive in that kind of way where it's like, oh, I'm going to write this in the from biggest to, or smallest to biggest. But guess what? We're not done. We still have another half of an equation to solve, remember? If we go back here, we still haven't solved sine x minus 1 equals 0. Oh, Mr. Kulik, this is going to take forever. Once you guys get the hang of it, they go really fast. You don't have to write out all the case stuff. I'm just doing it so that you can see it, right? As you get better at it, you can do it all in your head, I'm sure. All right, so I add 1 to both sides. So now I'll go look for where y is 1 on the unit circle. Go up to my unit circle. Where is y equal to 1? It happens here at pi over 2. And that's the only place. Oh, righteous, Mr. Gulick. So I'll just tack on that plus 2 pi k piece. And then start checking. So if I do k equals 0, that one spits out 2 pi. Great. If I do k equals 1, that's going to be 4 pi over 2. Making a common denominator here is okay if I do this in my head. Nobody's going to ask me in a minute, like, how did I get 5 pi over 2 here? I'm just checking. Good write is 2.5 pi also. And if I think about it that way, if I think about this as 2.5 pi instead, if I add another 2 pi, what's going to happen? Too big, right? So I'm not going to even bother trying k equals 2. Is everybody good with that? So we'll go start checking our negatives. So that's going to be pi over 2 minus 4 pi over 2, so negative 3 pi over 2. That's negative 1.5 pi. So I know if I subtract another 2 pi from that, I'm still going to be good. So let's go ahead and do it again. So that's going to be pi over 2 minus 8 pi over 2. So negative 7 pi over 2, or negative 3.5 pi over 2. If I subtract another 2 pi from that, that's going to be too small. So those are my only answers over here. So that list then is my total set of solutions for that problem. So again, I did a lot of writing here when I'm checking my K's. You do not have to show all that work, right? If you write out the general solution and then you just write out the values that are going to spit out of it appropriately, that is okay. Now, the first couple of times through, it's probably worth like writing it out so you get the feel for what's going on for yourself. But like after a couple of problems, it becomes like a gigantic hassle. You do not need to show me you doing this. I'll trust you to do basic arithmetic in your head. Is everybody okay? All right. So that's the gist of it. What I want, oh boy, from you guys, oops, don't do that, please. I'd like you to do like this set of odds and then this set down here. Okay? Keep in mind, for each one of these, you're basically solving over 4 separate intervals, so you're going to have 4 sets of answers. I tried to write them in an order that would be helpful, right, where you're looking for the stuff between 0 and 2 pi. And then you can use that immediately to write this infinite solution. And then with the infinite solution, you can automatically start generating the stuff. And if you look, there's even going to be stuff that overlaps between C and D. So you can use some of your answers from C automatically to fill in D. You know what I mean? Is everybody okay? Does this feel okay? This should feel pretty familiar. It's not unlike what we've been doing already. It just builds out a little bit on a skill that we've used before. Combined with like the algebra stuff that you hopefully are still feel pretty decently confident about doing from last year with quadratics there. Okay. That's it from me for today. Next time is going to be the review day. So if you are wanting to start early on your equation sheet or your note sheet, if you look at the first page of the test review packet, here's the test format, because this one's a little bit different than usual because you'll have some choices, right? 10 total questions. You only have to answer 8 of them. It's going to be 4 required solving questions. Or 4 required questions, 2 solving, and then 2 simplifying questions and 2 solving questions. And the other 6 are going to be trig identities. You can pick 4 of the 6.
So we have a test Monday?
Yes. So make sure if you're thinking about your note sheet, think about what's going to be helpful to you for this format of a test. I know there's only so much you can do with the trig identities in terms of like what notes are going to help you, but yes, yeah. So if you look at the the identity sheet that I issued you guys will be the same one that you get on the test. So it'll be it'll look like this one without the additions on it, right? So you'll have to remember those alternate versions. They weren't hard to make, but they won't be written on your paper already for you. You'll have to write them in yourself. Is that cool? Okay. I'm going to stop the recording now and let you guys start on your homework the last 20 minutes or so of class.